Electron energy. Energy and position are complementary. We've looked at this definition of kinetic energy before. Kinetic energy is 1/2 the mass times the velocity squared. So if we have an electron with a given energy, we can describe the electron's position in terms of not an orbit, which is like a planetary orbit around the sun, very predictable, but an orbital. It's a probability distribution map showing where the electron is likely to be found. And many of the properties of atoms are related to the energies of the electrons. So electron energy is important. So Schrödinger of the Schrödinger's cat experiment came up with an equation. It doesn't look like much right here, where, dang it, I should have looked up the name of this letter. The balance guy told me wrong the other day. That was phi, not upsilon.
Right, yeah.
You were right. I should have listened to you. You didn't speak up loud enough. Do you know what this one is? I don't either. Anyway, this represents a wave function. Very, very complicated, icky math that we don't have to talk about. We don't have to learn how to do it. So Schrödinger's equation allows us to calculate the probability of finding an electron with a specific amount of energy at a particular location in the atom. So this is like that pitching electrons, and mapping where they go. So solutions to Schrödinger's equation produce a lot of different wave functions that describe the wave-like nature of the electron. And if we plot that wave function squared, that represents an orbital. Just bear with me here. Calculations looking at the size, the shape, the orientation, and space of these orbitals are determined by 3 different integers that are plugged into that wave function. Those integers are needed to quantize the energy of the electron, because we know from experiment that the energy levels of electrons are quantized. Our experiments don't tell us much about what the electrons are doing there, but it does tell us that the energies are at specific levels. The emission spectra of different elements tells us that. So these integers are called quantum numbers because they are necessary to quantize the energy. So the first one is called the principal quantum number, and it's given the symbol n. Then we have the angular momentum quantum number, given the symbol L. I don't know why. The magnetic quantum number is m sub L. And then there's a fourth one that doesn't have to do with the energy, but has to do with the spin. And so this is called the spin quantum number. So we have N, L, M sub L, and M sub S. We'll talk about each of these. So the principal quantum number. When we talked about Bohr's model of the electron, we talked about different energy levels, 1, 2, 3, 4, etc. This N is essentially the same as the different energy levels in Bohr's model of the atom. So N can be any integer that is 1 or larger. N cannot be 0. It could be 1, 2, 3, 4, anything like that. If N is larger, then it's higher energy and the orbital is bigger. And so this works. So Bohr's model of the atom is not correct, but it's still helpful. So Bohr's model, we would see that as we go out, this would be n equals 1, n equals 2, n equals 3. The orbits get larger and the energy got higher, right? And that's the same with the orbitals. Orbitals are not orbits, but they are kind of like that. We can do calculations for hydrogen. The energy at level n is equal to minus 2.18 times 10 to the minus 18th joules times 1 over n squared. So if n is 1, you can plug that in. If n is 2, plug 2 in there. You can calculate the energy for an electron in each of these different levels for hydrogen. The energy is negative because the electron's energy is lowered by its interaction with the nucleus. Lower energy is more stable. As n gets larger, we also see that the difference in energy between levels is greater. So this is smaller. This difference here is smaller than this distance. So here's a diagram. If we're showing energy going up, here's the first level. This is for hydrogen. That is the energy of this. And n equals 2, we have a more negative energy. And n equals 3. I'm sorry, these are getting smaller. Because this is negative 19. So the energy is getting less negative. Yeah, right? It makes my brain hurt too. It's a higher energy because it's less negative. So like a higher altitude, it's like you're coming up out of the bottom of the ocean. You're coming up, but you're still at negative altitude, right? And the levels, the energy difference, never mind, I'm going to go on. Angular momentum quantum numbers. So that's L. So L can be anywhere from 0 to 1 less than n. So you look at a particular value for the principal quantum number, and that dictates what values are possible for L. Excuse me. So we typically only see these first 4 values of L, 0, 1, 2, 3, and these have been given letter designations. So if L equals 0, we call that S, L equals 1 is P, L equals 2 is D, L equals 3 is F. And those letters came about because they were descriptions of lines in the spectrum. So there was diffuse and principal and fine, and I always forget what S stood for. But they weren't random. We would probably like them to be A, B, C, D, but they're not. S, P, D, F. Then the magnetic quantum number specifies the orientation of an orbital, the direction in space that it is aligned relative to the other orbitals. M sub L can be anywhere from minus L to plus L, including 0. So the value of M sub L, how many of those, tells us how many orbitals there are of a particular shape. So if L were equal to 2, come on, pointer. If L equals 2, then M sub L can be anywhere from minus L, which is minus 2, up to plus 2. It's integers, so it could be minus 2, minus 1, 0, plus 1, and plus 2. So there are 5 different orbitals within L equals 2, and they have different orientations. Just try to hang in here, and hopefully we can bring it all together at the end and have it make some little bit of sense. This is very abstract stuff. The spin quantum number specifies the orientation of the spin of the electron. So electron spin is a fundamental property of the electron. All electrons have the same amount of spin, but some are positive and some are negative. So it is not the electron spinning like a top. But it's easier to think of it that way, and it doesn't do any harm. So think of this as being like there's 2 kinds of Beyblades. There's ones that spin clockwise and ones that spin counterclockwise. It depends on the launcher, right? So we've got plus 1/2 and minus 1/2. Just think of it as the electron spinning like a top in one direction or the other direction. That's not what it's doing, but it's easier to think of it that way and it doesn't hurt anything. Okay? So we call plus one half up and minus one half down. So to describe an orbital, or this region of space in which there's a probability that an electron is present, we specify all 4 quantum numbers. Well, the 3 quantum numbers describe one orbital, and then the spin, we'll get to that. So orbitals with the same value of n are in the same principal level, or it's often referred to as a principal shell. So these shells are kind of like, layers of an onion or something coming out, right? And they're getting bigger and bigger. That's the principal shell, and that is similar to Bohr's orbits. Within a principal shell, if you have orbitals with the same values of n and l, those are said to be in the same sublevel. So on these levels, there are also sublevels, or subshells. Well, finally, we have a picture, something to look at. So here's principal energy level. So for n equals 1, in n equals 1, the next quantum number is L. L can be 0 up to 1 minus n. Well, what's 1 minus 1? 0. So for n equals 1, L equals 0, and that's it. There aren't any other options. From L equals 0, m sub L can be minus L up to plus L. So if L is 0, m sub L has to be 0. So here we've got m sub L equals 0, and that corresponds to S. And so we call this the 1s orbital. This 1 is the principal quantum number, and S comes from the L equals 0. And there's only one of them. So there's only one orientation. If we go up to the second level, now we have 2 possibilities for L. L can be 0 or 1. When L is 0, as we saw, there can only be m sub L equals 0. L equals 0 corresponds to S, and so this is the 2s orbital. When L equals 1, m sub L can be minus 1, 0, or plus 1. So now there's 3 different possibilities. L equals 1 corresponds to P, and so these are 2 P orbitals. There are 3 of them. We go up to the third level. When n equals 3, we have 3 possibilities, 0, 1, and 2 for L. Again, for L equals 0, that's S, and there's only one of them. For L equals 1, that's given the designation P, and we have 3. When L equals 2, that's referred to as D, and now we can have minus 2, minus 1, 0, plus 1, and plus 2. So there's 5 different ones. So m sub L negative 2 has a different orientation than m sub L positive 2. Because if they had the same orientation, they'd be on top of each other and they'd be the same. And they're not, they're different. So in general, the number of sublevels inside of a level equals n. So n equals 1, there's 1 sublevel. N equals 2, there's 2 sublevels. N equals 3, there's 3 sublevels. Guess how many sublevels in n equals 5? There'd be 5, right? We can look at the number of orbitals within a sublevel as that's going to be 2L plus 1. Actually, we end up using these so frequently that we just remember it's 1, 3, 5, and the next one's 7. 1, 3, 5, and 7. The number of orbitals inside of a level is n squared. Actually, I don't find that very useful at all. Any questions? Okay, list the quantum numbers associated with all of the 5D orbitals and how many of them exist. Well, let's just start with n. So what is n for a 5D orbital? It's 5, right? And then the next quantum number is L. There's lots of possibilities when n equals 5, but the letter D tells us what L is. So when L is 0, that's S, 1 is P, 2 is D, 3 is F. So L equals 2. The next one is M sub L. M sub L can be anywhere from minus L to plus L. If L is 2, it could be minus 2, it could be minus 1, 0, 1, or 2. So we can describe one of these orbitals as 5, 2, negative 2. And have 5, 2, negative 1, 5, 2, negative 0. 0, 5, 2, plus 1, and 5, 2, plus 2. All of these orbitals have the same principal quantum number and angular momentum number. It's M sub L that's different. So how many different orbitals are there? There's 5. There's 5 of them, not because it's 5D, but because it's D. Any D sublevel is going to have 5 different orbitals, because when L equals 2, we have 5 different possibilities here. Another practice question. So each set of quantum numbers is supposed to specify an orbital, but each of them has one quantum number that's not allowed. Replace the quantum number that is not allowed with one that is allowed. So in A, we have n equals 3, L equals 3, and M sub L equals plus 2. Well, can we have n equal to 3? Sure. If n is 3, can L be 3? No. It can only go up to 1 less than 3, right? So L would have to be 0, 1, or 2. But we're also told that M sub L is plus 2, and so that restricts this. There's only one possibility. What does it have to be? It has to be 2. So this should be 2. For n equals 3, L can be 0, 1, or 2. We're choosing 2 because M sub L is going to go from minus 2 to plus 2. We need the plus 2. If we chose 1 here, then this wouldn't be allowed. This is like some weird logic puzzle. Okay, let's look at B. So we could have n equals 2. Is L equal 1 allowed when n equals 2? Yeah? So if L equals 1, can M sub L be minus 2? Nope. Because M sub L is minus L up to plus L. So it could be minus 1, 0, or plus 1. So this is the one that's wrong. And we're supposed to replace it with one that is allowed. So here we have 3 choices. We could choose minus 1, 0, or plus 1. 0. 0 works. Okay, letter C. N equals 1, L equals 1. Is that okay? No. L goes up to 1 less than n. It starts at 0. So if n is 1, L has to be 0. If L is 0, can M sub L be 0? Yeah, it kind of has to be. Understanding this sort of stuff with the quantum numbers is super helpful. It is not critical to passing the class. Okay, you can get a C in this class without really grasping these quantum numbers. so don't freak out. So let's use this to explain atomic spectroscopy. So each wavelength in the spectrum, those different colored lines that we see, corresponds to an electron transition. Electrons moving between two different orbitals. The atom absorbs energy, and then the electron moves to a higher energy orbital. That excited state, because it got excited, it went to higher energy, just like children, when they're excited, they're high energy, right? The excited state is unstable, just like children on a sugar high are unstable. And eventually the electron is going to relax back to a lower energy level. It doesn't necessarily need to be the one it came from, but just something lower. Sometimes it'll take several steps back down. When it does that, the energy that it absorbed has to go somewhere. It's released, and it's released as a photon of light. The energy of that light is equal to the energy difference between the orbitals. Energy diagram here. Energy increasing. Here we have n equals 1, n equals 2, n equals 3. I just realized I've been doing something wrong for about a week now. As the energy levels get higher, they get closer together, not farther apart. I don't know what I was thinking. Anyway, if we excite an electron from n equals 1 up to n equals 3 by zapping it with electricity, perhaps, giving it energy, it goes up here. It can't stay up there. It will eventually come down. Maybe it'll come down to n equals 2. It's losing energy when it does that. That energy has to go somewhere. The energy is released, and it's released as a photon of light, and the energy of that photon corresponds to the energy difference between these two levels. For the electron to go from a lower energy state to a higher energy state, it has to get just the right amount of energy. It's like exact fare on a bus. You can't give them too much. They won't take it. I don't know. Do they still do that? Maybe that's a super old analogy. They'll take it? It used to be that they would only take exact change, which was really stupid, because I just want to get on the bus. I don't care if it's $5. I just need to get on the bus, right? So I need to stop using that analogy. But the amount of energy has to be just right. And it has to correspond to the difference in the energy states. When electrons go to higher energy states, they're unstable, and they tend to lose energy and go down to lower ones. So when it's in a higher energy state, it has a higher potential energy, and just like physical objects with high potential energy, it's unstable. Think of that 10 kilogram weight on top of the roof, right? If you give it a little nudge, it's going to fall. It's unstable. If you put something like that on the sidewalk and you give it a little nudge, is it going to fall? No, it can't, because it's already on the ground, right? So its potential energy is 0 in terms of elevation. So at the higher energy state, it's unstable. Anything with high energy tends to be unstable and go to a situation where it's lower in energy. So those excited electrons will transition to lower states, and they will emit the energy that they lose in going between those states. Each line that we see in the emission spectrum corresponds to a difference in energy between those two states. So we can predict the lines for hydrogen. Hydrogen's nice and simple. It only has the one electron. So we can calculate the difference in energy between any two states, because we have that nice equation. For an electron in some energy state n, there are n-1 states that it can go to, right? So if it was on the third level, it can go to the second or the first, right? There's only two possibilities. So it can generate n-1 lines. So if it was on the third level, it could generate 2 lines. It can't generate any more. And the Bohr model and the quantum mechanical model both predict those lines very accurately for one electron systems, which is hydrogen. So the change in energy is the energy of the final state minus the energy of the initial state. And we said earlier that the energy of an electron in hydrogen is minus 2.18 times 10 to the minus 18 joules times 1 over n squared. So the energy for the final state is this right here. The energy for the initial state is this right here, where this is n for the initial state and this is n for the final state. So we can factor out the minus 2.18 times 10 to the minus 18 and get 1 over nf squared minus 1 over ni squared. So the change in energy for the electron or the atom itself is going to be negative because it's losing energy. The photon that it loses has energy, but its energy isn't negative. It's positive because it's the energy that's leaving the atom. So the change in energy for the atom is the same as the change in energy for the photon, but they're opposite in sign because one's gaining and one's losing. And we also have this relationship, lambda equals hc over energy. And we can use that to calculate the wavelengths of light for different levels. We're going to be doing some calculations with this in lab today. Aren't you excited? Okay, so here, looking specifically at hydrogen, here's n equals 1, n equals 2, 3, 4, 5. You can keep going up to n equals infinity. That would be ionization, where you've excited that electron so much that it actually left the building, right? It's gone. So if we have an electron in level 5, it could transition to 4, that's not shown here. It can go to 3, it can go to 2, or it could go all the way back to 1. So this difference in energy corresponds to an ultraviolet wavelength. This difference in energy corresponds to a purple light with a wavelength of 434 nanometers. This transition here corresponds to infrared wavelengths. So wavelengths that are too long for us to see with our eyes. Going from 4 to 2 gives us this sort of green line at 486 nanometers, and from 3 to 2 gives us 656 nanometers, a red line. So these are the 3 transitions that give photons of light within the visible spectrum. So that's what we see when we excite hydrogen and separate the wavelengths that are emitted. We see 3 lines. There are other things being emitted, but we can't see those. Could we detect them? Yeah, but just not with our eyes. Any questions? We're going to observe this part today. We're going to look at a hydrogen lamp with a spectroscope, and we're going to see these lines. Determine the wavelength of the light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. So the initial is n equals 2. That's where it's starting. The final is n equals 7. We've got this delta E equals negative 2.18 times, it was 10 to the minus 19, right? 18? I thought that was too nice with the 2.18, but joule seconds. 1 over final squared minus 1 over initial squared. So we could calculate the energy of this, right? We're looking for wavelength, but wavelength is related to energy. So we can plug the numbers into this. It's not joule seconds, it's just joules. I was wondering how that was going to work out. Just joules. Final is 7. 7 squared is 49, so maybe we'll just do that in our heads. Minus the initial squared, 2 squared is 4. So it's another thing entirely to get your calculator to do this. On my 36X Pro, I'm going to go minus 2.18 EE minus 18 times, open parentheses, 1 divided by 49 minus 1 divided by 4, close the parentheses, press the equal sign. So delta E is 5.01 times 10 to the minus 19 joules. Why is that a positive number? Because it's absorbing energy. So light shining on this hydrogen atom, it absorbs 5.01 times 10 to the minus 19 joules to bump 1 electron from n equals 2 to n equals 7. So what's the wavelength of that? Well, the wavelength is equal to hc over E. So we know what E is, and we know what H and C are. H is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. That's where the joule second was. Speed of light, 3.00 times 10 to the 8th meters per second. There's the seconds canceling out. And then down here, we've got the energy we just calculated, 5.01 times 10 to the minus 19 joules. The joules are going to cancel out, and we're going to be left with a unit of meters, which is good because wavelength is a length. 6.626 times 10 to the minus 34 times 3 times 10 to the 8th divided by 5.01 times 10 to the minus 19. So 3.97 times 10 to the minus 7 meters. Any questions? This equation, or something very similar to it, would be given on an exam. Planck's constant, the speed of light would be given. This equation would be given. You have to figure out how to put them together.